So, good morning everybody. First of all, thank you Manfred for organizing it. I'm the first speaker, so on behalf of all the speakers, thank you for inviting us, giving the chance for the exchange between the professional and the amateurs. We discussed yesterday, it's an important step to bring the two worlds together. It's one world, but every world has different countries. So I think this workshop is a good opportunity to bring together for exchange, to know what both sides want, what they can offer, what they need. And my talk today will be about one thing that I think can be done easily, one by the professional side, but also on the amateur side. And I will be talking about near EOB spectroscopy. The other thing that we discussed before is that each presenter should explain himself, introduce himself. So this is a picture of me in my usual work environment. Oh, you don't see. This is a big dome. This is me. This is Lord Palmer. I'm a lecturer at Graz University, which is quite close to here. But I did the typical tour in modern academia with my diploma from Vienna, PhD in Leuven in Belgium, my postdoc at the French Nuclear Commission in Paris, and a research fellow on Tenerife. And this is the picture showing me in front of the Mercator telescope of the University of Leuven, which is a 1-meter telescope. It's a small telescope, but the spectrograph that is sitting roughly here is one of the best in the world, with a resolution of 100,000, and this is my choice of instrumentation. However, what I'm going to talk about can be done at 100K as well as 5K, which is simply UV spectroscopy. Okay, it's not working at this distance, so I will choose this side. If we look at the sun, what do we see? What do we see? We see the atmosphere. And here on the left side we have the photosphere, on the right hand side we have the chromosphere. But the atmosphere has one giant disadvantage. It's hiding everything that is below the atmosphere. But to understand the atmosphere of a star, what we need is to know the structure of the star. And Manfred was kind enough to hand out some stellar models.
I'm sorry, it was set to wrong.
Yeah. So yesterday, or with the registration, Manfred was kind enough to hand out little stellar models for your expectation, which is actually a pretty accurate model of a star. If this is the sun, so I ask you now to have a little bit of fantasy. If this is the sun, we have the core, we have a radiative zone, we have a convective zone. And the atmosphere, so from inside to the outside, the sun has about 700,000 kilometers radius. So 1.4 million kilometers in the diameter. The atmosphere is just a couple of thousand kilometers wide, which comes pretty close in comparison to the aluminum foil. So if you want to picture it, the atmosphere, the part we see, is about as thin as the aluminum foil of your stellar models when you have them. So please appreciate science when you snack. The point is, the atmosphere is giving nearly 100% of the flux. We have the photosphere, which gives nearly 90% of the whole flux. And in particular, in the optical range, even more. except I think a handful of lines. All the other millions of lines we see in the spectrum are from the photosphere, except the magnesium K line, everything basically, and H alpha, everything is photosphere. The chromosphere, which is the layer above, and I will show you in a moment where we are located, is giving 10%, but mainly in the UV and in the infrared. So now my expertise actually is not the spectroscopy, but getting to know how the structure is. And I would like to know, how would you look beyond the layer that you cannot look through? Any suggestions? How we could empirically probe the structure?
Pulsation.
Pulsations. Well,
Yeah, astroseismology.
Astroseismology, thank you. My students always laugh when I manage to navigate a lecture to the buzzword astroseismology. I did my PhD in seismology of solar-like stars and red giants. And we could measure the core density as well as the core rotation. So, but this is my part, and we need spectroscopy, and to better understand the model, we also need spectroscopy. And this is how I got into spectroscopy during my postdoc in Paris. But the thing is, so you can empirically, so you can calculate it, and you can know roughly the structure. You know that, I think that's the next slide. Something's not working here, yeah. So simply from models, we know that the mass of a star is very much governing how the structure is built and the pace of evolution. Here's a diagram. It's my favorite diagram in all astrophysics. It's called a Kippenhahn, which in this, you have the mass coordinate of the star, which is normalized, so you can compare many stars next to each other. And here you have the mass of the star. So we can compare the mass of a 1 solar mass star with the mass of a 20 solar mass star, because it's all normalized. And, you know, astrophysics, everything is normalized to 1 or the sum. It's that simple. Now, what you see in that diagram is, here you have convection. The red stuff marks convection, and Kippenhahn was very creative. In the first diagrams, when he drew that, it might remind you of a sheep or an elephant. And he actually drew that in the professional publication. He drew little animals in there, in the convection. So this part is convective as much as this. Now, this diagram here shows you a very fundamental difference between low mass stars, which are here, and high mass stars on that side. What is it? What is it? A question to the audience.
Convection zone.
Yeah, where? Where is the convection zone?
It's on the outside in the low mass stars, it's inside in the high mass stars.
Exactly. And the physics behind that is very different. Because this point here is the partial ionization zone of metals. When do metals start to become only partially ionized and the material becomes opaque for radiative transfer inside this layer? And when the material becomes opaque and radiation cannot do the trick anymore, convection kicks in. Basically taking the mass balance and moving it physically for 2 pressure scale height until the next one will move it. And so we have a cascade from here moving the heat, energy, chemicals, and angular momentum up. In the sun, a photon needs for this distance about 100,000 years. For the rest, it takes a few months, because convection is so much more efficient. And as we go to, those are the late type stars located here in the Hertzsprung cluster diagram with the, in this case, the color index on the x-axis and the luminosity on the y-axis. So those are the late type stars I will be talking about for the rest of my talk. So this is because the temperature gradient at the star gets cooler and cooler. So this point is moving inward, and towards low mass stars, we go to nearly fully convective, which is the lower limit for a star. If we go to the higher mass stars, and this is, we are moving up the main sequence, then we have more efficient fusion from hydrogen to helium. This here is done via the proton-proton chain. This is actually then done through the CNO cycle, which is much more efficient. Therefore, we have, and because it's so efficient, convection is needed to move the energy out of the core. So we have a convective core for more massive stars, and everything outside is radiative. Now, why I'm stressing stellar structure here? Because the cool stars, they have a chromosphere. So if you look into the chromosphere of in the atmosphere of late type stars, so what I showed you here is referred to as the stellar structure. But on top of the stellar structure, we have the atmosphere, which for a star like the Sun, something is not right here today. For a star like the Sun, we have here we have the stellar structure. So here we start just at the surface. We have the photosphere. Then in blue we have the chromosphere, the transition region, and we have the corona. So this is in kilometers. Remember, the star itself is 700,000 kilometers wide. Those are a thousand kilometers. I'm not good in mathematics. I'm just an astrophysicist. So you can do the math, but I think it's even thinner than the aluminum foil. This diagram looks quite complicated. We have the distance to the surface, and we have the temperature. And this solid line here is showing the temperature profile in the stellar atmosphere of the Sun, or any cool star. And there's something, how should we say, something counterintuitive. Because the temperature minimum, we would expect far outside. But the temperature minimum of the Sun is actually 500 kilometers above the surface, where we are on the order of, well, about 6,000 Kelvin. And then something strange happens. We have an inversion. In the chromosphere, it's heating up. And then we hit the transition region, and then we go into the corona, which is off the scale. I think it's 1,000,000 Kelvin in the corona. So if you now ask me why, I can tell you we don't know. There's a lot of ongoing research to understand the temperature profile. Different heatings, magnetic, jets. I would then simply refer to the other half of the department in Graz, because they do all the research. Hanselmeier, Veronique, Temmer, they all are trying to research this profile, which is not yet understood. What else you see in this diagram are regions where lines are formed. For example, you see this is H alpha. H alpha, the core of the line, is formed further out than the wing. The core is further out than the wings, but in this case, the core is formed mostly in the chromosphere, while the wings are formed in the photosphere. And this is something astrophysicists like, because if we have an effect like a temperature gradient, and we have one parameter we can measure, and we know one quantity is formed at one region, and then in the other, we actually can work differentially. We can try to reconstruct that profile in the star. As I say, so just already mentioned, the photosphere is actually mostly contributing to the optical, purely contributing to optical. The only lines that I think are notable is the magnesium triplet at 518 nanometer and H alpha. In the UV and infrared, you see more lines in the chromosphere because it's hotter, and so you have higher ionization states. Yeah, so I already was talking about the temperature inversion, and there's one line that is particularly suited for studying that temperature variation. And this is the, oh, it's really not working today. It's the calcium K line, a calcium H&K line. It's once ionized calcium, which is mainly formed in the chromosphere, but still has some contributions in the photosphere. And it's sampling, in particular, it's sampling that main temperature gradient. And if you ask me if those lines are sharp, no. I tried to search for a diagram where they are marked sharply, I didn't find it. So don't nail me on those values. So, but the calcium K line, calcium is a very abundant element, and if you think of, well, for what we call metals, but if you think of the periodic table, it's on the left, which means it is easily ionized because the outer electronic shell is not well populated. So it's very efficiently ionized in the chromosphere, and if you look at the relative line strength of absorption lines as a function of the spectral type, you see that by far in the late type stars, FGK and further down, calcium 2 is the strongest line. If we go hotter, hydrogen will become more the strongest line, but in late type stars, it's really calcium. And I would like to prove that to you. Here's a spectrum of the sun as a star. Can you spot calcium H&K? Where? You point my laser.
Up there in the top left side.
Yeah. Yeah. You see how strong they are. And they are not the only calcium lines seen. So this is a spectrum I took some years ago, and I can tell you, observing the sun as a star is not trivial, in particular if your telescope is 1 meter. You have any idea or any suggestions how I should do that?
You can filter in the infrared? Put in a filter in the infrared?
No. A filter would interfere with every measurement. We want to be as pure as possible with the night instrumentation.
Close the covers. Close the covers of the mirror.
So my first naive estimate was I just wait for the sun to set and then start another point at the night sky, at the dawn. And I can tell you it didn't go well. I got spectra, but the spectroscopists I was working with told me no.
Well, use it as people in Potsdam do. Use a very small telescope and a fiber and connect that to the big spectrograph.
I want to use the same telescope.
Yeah. Okay.
And I don't want to burn the fiber and the spectrograph.
Reduce the aperture.
All of that, so the night sky I was later on told when I showed the diagrams, is we get some scatter between, dependent on if the sun is here and I take the point there, the angle between my source is introducing some line asymmetry due to knee scatter. There was something back then. So the only way is we need a point source. And the best point source in the solar system are either asteroids, and one of the brightest one is Vesta, and the other one is, or the best standard is the Jovian moon Europa. Why? It is basically a white flat mirror. Even good for polarization experiments. We didn't go that far, but so and suddenly you have to expose not for 0.1 seconds, but you have to expose for about 10 minutes, because your sun suddenly is a 5th magnitude star. So, and if you are working at high resolution, this is about 90,000 in spectral in spectral resolution, and going from the near UV into the near infrared. So from 390 nanometer to 900 nanometer. So that's a pretty region, a pretty far region. What I did was to take two objects and I did some back-end pipeline, because you don't want to reduce in the shell spectrum over 50 orders. You don't want that. I did in my undergrad, I did 20 orders for a couple of thousand spectra. No, you don't. A couple of gray hair come from that. So this is actually now with the Hermes spectrograph, the spectrum, the image I showed you before, which is a spin-off of the Harps spectrograph, done by Leuven University with Brussels, Liège, and Geneva, and Tautenburg. I had 2 point sources. They all were reflecting the same object, the sun. But because they were different radial velocities and had a different barocentric velocity, if I shifted them for the radial velocity, many lines, they appear to be the same, and that is the ratio. So there's a little bit of difference, but basically it's centered at 1. What are those?
Atmosphere.
Atmosphere. Telluric lines, because they were imprinted on the spectrum, and when I shifted, but at different velocities than the lines. And if I shift on the lines and divide, they are suddenly out of place. And if I divide one point source spectrum by the other, then they will give me big residuals. And when you have this huge deviation, those lines are tellurics. That diagram is on my desk, so whenever I'm working with a line and get excited, if I have just found another binary, I better check if this overspectrals are tangling. You try to avoid those regions. Fun fact, if people try to observe exoplanet atmospheres, well, they search for an atmosphere very similar to ours. They are just interested in those regions. And so they have this dichotomy, or this, I don't know, nearly pain. They need to correct for that. So it's difficult. I think there are a couple of, a dozen or 2 dozen of stars where it's working so far, but the big game changer will be James Webb Telescope, because there's no Earth atmosphere. You don't have that. So if they see a line, they know it's there. So this is the spectrum. So we identified calcium H&K up here. But further down, you also have some very strong lines at about 555. 1, 2, and 3. And they are also calcium. This is so-called calcium infrared triplet. And I don't know where, it's not as, the region where it's excited is, I think, not that fully in the chromosphere, but it has similar characteristics, as I will discuss for the rest of my talk. Here we have H alpha, beta, gamma, delta, epsilon. So, what is, here we have calcium K and H, but H is blended with the Balmer line. So for this reason, I will focus mainly on calcium K because it's unblended. But it comes with, for this purity comes for a cost. Because each spectrograph, well, we are already in the very far blue. Everything is against you, even going from by a few nanometers further to the blue. Everything is against you. It's the atmosphere is eating up that blue more than that. Your CCD is even less sensitive already, and then fiber, your glass fiber, typically is also not very, doesn't like blue. So, and if it likes blue, it was very expensive, which this glass fiber was. And then, of course, you even have the spectral blanketing. So this one typically has a lower signal to noise than this one. It's a bit of painful, but yeah, and the other one here. Wait, where is magnesium triplet? 518 here. That's the magnesium triplet here, which is a very good indicator for late type stars, for masses, for temperature, for the fundamental parameters. As I said, I'm now focusing on the calcium K line. And this is it. This is the behavior. Remember, we saw a big V. But if we zoom in, what we see, this is about what we see in the sun. But it has some structure in there. And if we go to different targets, what we find, for example, HD 73256, what you see is a big spike. And look, here's a pseudo-continuum. Those spikes go beyond even the pseudo-continuum. What is ongoing? What's happening? Now, calcium K, because it's the way it's formed, has actually a very interesting. Calcium H and K have a unique feature. This one. We go to this. We grab one of the profiles and try to understand it. In red, I show the V profile, which comes from the photospheric contribution of the light shape. However, most of it is formed in the chromosphere, and the chromosphere is hotter. And we all know that luminosity goes with the fourth power of temperature. So if we are hotter and have enough optical thickness, we actually can produce something that is brighter. Now, looking at an image of the sun pretty much a month ago. So this is from my university. University of Graz is operating an observatory in Corinthia, the Kanzelhöhe Observatorium, which is a member of the global network to monitor the sun in white light, H alpha, in K, and I don't know, since 50 years, every day they draw a map of the sunspots. This is continuous. So here I show you an image which is colored blue because it shows you a full disk of a high resolution image of the sun in calcium K. And here we have the same effect. We have dark spots which correspond to to the photospheric dark spots, but we also see a network of bright regions, which are bright spots, so they contribute to the flux in that wavelength. And they are the so-called plage regions. I'm not native speaker, so perhaps we could discuss if the pronunciation was okay. But those are the active regions. And they contribute to the flux in calcium K. And the contribution we see sticking out of the photospheric contribution here as the double spike profile. So now we want, this is a quantity of the chromospheric flux contribution. The question, and this is actually a proxy of magnetic activity. If we try to do that with another star, we wouldn't see anything, because a star on the fiber is integrated to point source. We lose any spatial resolution. But this we see. So we can even, and counting spots is very difficult because we need a time series. And then we need to do some modeling. And so we could reconstruct the filling factor on how many spots are covering the star, which is not easy, in particular for main sequence late type stars. However, here, in the surface of that feature, we have a good quantity. It's an unphysical unit, but we have a quantity and we can compare stars by each other. One thing, this is difficult to describe, but one thing that we know for sure is that the width of this feature is indirect proportional to the surface gravity of stars. So if the star becomes a red giant, surface gravity will go down by several orders of magnitude. The Sun has log G of 4.4. On the red giant branch, we have 2. So on Earth, by the way, we have 1, just to put things in perspective. So there's a lot of astrophysics. And just yesterday, I was talking with a colleague of us, Luca Fossati, who is also working on this feature for his exoplanet research. And if I would have counted how often we use the term, this is not known, that is not known, probably I would have run out of fingers on hands, because it's a very challenging theoretical question to model that feature. And this is what astrophysicists call job security. So this is now the picture, as I said, and the question is, do we have, if we reduce that to point sources, what do we get? If we integrate the disk, each disk over to a point source for one epoch, we get one value, one flux value, and then we could actually do some color indices. Not very satisfying. We need to come up with a different solution. And people realized that somewhere in the 50s or 60s. And those people were at the Mount Wilson Observatory, and you might have noticed that since the 50s, instrumentation has changed slightly, which is, back then, they did that with photographic plates. Later on, with photomultipliers. Now we use high-resolution spectrographs, or low-resolution spectrographs. So there must be some continuation. And what I'm showing you now actually is a formalistic workaround to mimic the combined response of, I think, a photomultiplier plus a filter back in the days. So now what we do is we can take spectra, but at the time when they were using photomultipliers or photographic plates, all you had was a point source. And this is called the Mount Wilson SIndex, which I show you here. Now, so MWO stands for Mount Wilson, and it's a bit, so it looks pretty simplistic, and it is. The catch comes in a bit. So what we have here is the spectrum in the near UV. And we have the normalization. Let's start with the obvious one. We have L and R, which are those boxes. We integrate the surface under the spectrum in the left and the right box. And that's and then the sum is normalization. It gets a bit trickier when we come to calcium H&K, because you see here, you see this triangulum. This is a triangulum filter with a full width half maximum of 1.09 angstroms. So that's a that's a narrowband filter. Probably interference filters, very narrow, very precise. So this is what they put in front of the photomultiplier, and this is the filter curve of the filter and the photomultiplier. At the time, well, the big difference between photomultiplier tubes and CCD is that photomultipliers are actually very blue sensitive. And so that's why they could do it already in the 50s and 60s. So this triangular filter is mimicking the response curve of the instrumentation at the time. And they had two, one centered on calcium H, one centered at calcium K. And you simply take the spectrum, fold it with your filter, and you get what you see here as the magenta curve, and you integrate over that. So you have 4 values, and you get a fraction. And that's the point why we are talking here about it today. If we have a filter of 1.09 angstroms at a wavelength of 400 nanometers, that is a resolution of about 4,000. And that is easily doable with a small spectrograph on a 20 centimeter telescope, if you want it. And the funny thing is, and that's another, we don't know why it's working, it doesn't need a proper normalization. There are several theories why it's working, but there is no, the leading theory is that this actually is taking care of the slope. My colleague was telling me that he screwed up the spectrum on purpose and still got out the same value. So this is a slope normalization factor. Now, this instrument is, so there's another factor we haven't discussed yet. Because this value, this SIndex, is highly dependent on a lot of parameters. It's the spectral type, it's the metallicity, it's the spectral resolution. So you need to calibrate your instrument towards basically each group of targets, and you need to have your instrument calibrated. So if you take the same targets with different instruments, you will get different S values. And because Mount Wilson was observing the same targets for decades, they became so massive that basically they represent their own standard. It's a completely independent, undimensional instrumental value, but because they have so many, everybody tries to be consistent when comparing to Mount Wilson. So what you do, what you do is simple calibration. You take the values they publish in the paper or you get from the database, and you take about 10 targets. And you look up what is the SIndex Mount Wilson is getting. You put them on your fiber or your slit. You get your instrumental SIndex, and you plot them, and then you fit a line through, and the slope of the line, that's your alpha. So congratulations, you just put yourself on Mount Wilson standard, and now please don't touch your instrument ever again. Because whenever you change, like a grid or the annual aspect of your grid, you will change your resolution. So you have to redo alpha. So that's, of course, is well done for fixed instruments. And I thought I had a fixed instrument until I came back to La Palma in 2018, and the engineer told me, great news, we just upgraded our fiber. It's now more blue sensitive and has 5000 K more resolution. Yes! I have to redo that again, or simply repin my spectra to the older one. So whatever I do, I still have to do it. But yeah. And why is there actually an error bar on that? Any idea? Why is an error bar an activity?
Maybe variability?
Let's call it magnetic cycles. Stars, the sun, has cycles. And this is you don't get one value, so you need to take that into account.
Is wind a factor? Solar wind? Doppler shifted?
That's too small. So now we are still in SIndex. If we work in a very narrow bin, like I do, I work on solar analogs. So they all are by definition same mass, same radius, same temperature, therefore same color and same oscillation parameters. That's how they were selected. So I don't need to move out of the SIndex box. But if I want to make it wider, if I want to compare solar analogs with K-tools, then I need to take into account the metallicity. If I want to go on a different grid, I need to take out the color contribution. And that's what we do with the log R H&K. And if we want to know what is the contribution of our photosphere, then we go into log R prime. And now this is, I apologize, this is astronomy at its best. We still use partly scaling relations from 1984. I just, for your reference, I put you here the scaling relations and how you can convert from the measured temperature to a color index. The color index is parameterizing the effect of the stellar temperature in Johnson. So what is, ignore please everything below the second line. What we do is we calculate the combined value for photosphere and chromosphere, and then due to scaling relations, we calculate the value simply expected for the photosphere. And the difference, by subtracting that, we get a value based on our measurement for the chromosphere. And now, what does it tell us? This is a value, again, note that, and here somebody did an update recently, because now astrophysics of course got better over the last 40 years. But this is simply for you if you want to do it and want to do the math, we can talk later about it. Now, we need to put things in perspective. This value is dimensionless. We need to put it in perspective to have some astrophysics, some astrophysical interpretation. And what we get, there's a theoretical limit. It's called the Basal Flux, which is a log R prime of minus 4.1. Here in the literature, I forgot the log, so this is still log. So you see all the values, they are higher than minus 4.1 on that dimensionless scale. This means with those scaling relations, the quiescent photospheric contribution, so no Lshape region, simply the normal flux without any activity is -4 of -5.1. Now there are three reasons why we could find a value below. One is your data is bad. We were talking about the signal to noise issue. One is you did something wrong in the instrumentation, in the reduction, or we found an exoplanet. So Murphy says typically it's one of the two up, but yeah. The other thing is if it's really done well. My colleague told me that the detection rate for well done photometry on sub-basal flux for exoplanets is nearly 100%. Why? Because they have atmosphere and they have evaporation and they are eclipsing. So the gas is eclipsing the star, and if they have calcium, you have additional absorption. So, yep. But before you publish a paper, better verify with additional data before you publish another. Obtain radial velocities to get the orbit. That's the best and solid response. Now, what is the scientific interpretation? And I thought that I'm here after about 20 minutes, so I will now rush through that part. There's a paper published in the year 1972. It might look old, but this is 50 years ago. And the paper is, in the meantime, canonical. I think it has 2,000 citations. That's one of these papers sticking out. They just had, this February, they had a conference to celebrate that paper. And if I'm saying that paper, that figure, because the figure is the title, that figure and a caption. That is the famous Strumanich paper, 1972. What does it show? You have the age of a star here, and you have a dimensionless quantity here. And you have the rotation of stars as it slows down as the age. From here you have 1 mega year, 1 giga year, 10 giga year. So that's the end of the beginning and the end of the main sequence. Stars are slowing down. And as we are still in the late type stars, so we have a convective region. So rotation can trigger or will trigger a dynamo. So we will have activity. As rotation slows down, we also have the activity here measured on the calcium, what we just discussed, will slow down. I will not go into lithium, because lithium is sold as a magic tool, but it's not. If you want to know more, ask me. Now, why is it happening? This is the so-called Kraft break, and I wanted to take the original paper from Kraft in 67, because he found that stars of about 1.5 so here we have a Hertzsprung-Russell diagram, basically. And he found that stars more massive than, or less massive than 1.5 solar masses, they rotate very slowly, and even slower as we go to lower masses, which is indicated here. And above that, they rotate very quickly. This is connected to the convective envelope and the magnetic winds driven by the convective envelope, taking away the angular momentum and slowing down. In the meantime, we found a fancy word for it called gyrochronology, and this is how it works. You have this cloud of data points represents one cluster, one open cluster, and on the y-axis you have the rotation rate normalized to the solar rotation rate, which is shown over here. The x-axis is the age of the star. So why use clusters? You have a whole bunch of stars at the same age. You don't need to worry about, on that scale, the dispersion is zero, is negligible. And what we see is that cluster, and you can determine the age very well simply from the turn of point. And what is now a hot topic for the last 10, 15 years is to see, well, people found that very young stars have a very large dispersion, and those are the, I think, the 10th and the 90th percentile, showing how rotation is evolving. Focus on the solid line, which is the surface rotation. You see that at 1 mega year, 1 million years, you have a very big dispersion. But it's constant, because you're still in disk locking phase. At some point, about 2-3 mega years after evolution, the star started, the disk is detached from the star, and when the star is contracting, the star is spinning up. Simple experiment, like when you're on your office chair, you spin up when you pull your arms together. Those stars are still contracting, and they will spin up. And they will spin up for about a few mega years, and it's not understood yet where they are. The dotted line is the core rotation. You see, we have a high level of differential rotation between core and surface. And up to 100 mega years, there's a very wide range of rotation. But between 100 and 1 gigayear, they magically come together. And at 1 gigayear, they basically are degenerated, and they evolve all together down. And that is the effect of the magnetic wind, taking away little angular momentum, slowing them down. It's so accurate that you actually can measure the rotation rate and determine the age. But in astrophysics, nothing is as simple as it seems. So there are some catches, but that takes a couple of nature papers to explain. Now, coming back to the activity, what we see here is a diagram by Pace. It's called the L-shaped diagram, where you have the age on the x-axis and log arc. This is the, well, as we just learned, the chromospheric contribution alone. And you see that young stars, up to 2 gigayears, have a very wide range of activity. But people try to argue that this is an age indicator, but, well, the scatter in the young ones even bigger, in the minimum and the maximum, than on the main sequence. And that scatter is the typical width of the solar activity. So now there people used Mount Wilson data to look into not only, and if you have a single measurement, well, you're somewhere. But if you take long time series, and please look at the x-axis, the 60s till 2020. This is Mount Wilson data. What people see is that you have variations, you have cycles. And the thesis I'm citing here I have here for if you want to read it, based on Mount Wilson data. Because it was a whole story how to get them. Somebody gave them a call and said, I have a lot of magnetic tapes, you want them, otherwise I trash them. And it turned out it was the missing two last decades of Mount Wilson data. So that guy took a plane, took the magnetic tapes, and digitalized them, and wrote his PhD thesis about it. So what he found, what Ricky Engeland found, was that, and the team around Travis Metcalfe, that it's more the period and the amplitude that is indicator for the age. And there's another diagram that was done by Böhm-Vitesse in, I think, 2007, where they compare the rotation activity, the rotation period, which you can get from spots or Ca H&K, and the period of the activity cycle. The sun is here, 11 years, but it's just in the middle between two branches. One is the inactive branch here, and the other one is the active branch, where, no, just the other, yeah, it must be there's the inactive branch and there's the active branch, and the sun is just in the middle. This is not understood yet. Another we don't know, called the sun in the middle or sun in transition problem. The latest research shows that, suggests that actually there is a transition that stars get active, are active first, and at some point move off to the inactive branch. Why? We don't know. There are some models suggest that the sun is just about to invert its rotation profile from what we call solar, being faster at the equator than the cold antisolar, which would flip. It's a theory. So a lot of research is ongoing on 3D modeling, 2D modeling of the rotation profile. Here's just another diagram that I've done. This data point was me being a goofy PhD student in 2010, getting my first spectrum of θ1 tau, and this is 2018. So what you see here are in red is the SIndex of θ1 tau, red giant binary in the hierarchies, and what you see, this modulation here, that is the rotation, because the spots, they move into your field of view and move out. And on red giants, you have giant large regions. You don't have those little tiny cute ones like on the sun. You have giant ones, where the star is. That one is about 20 times bigger than the sun, so the regions are bigger as well. So you see here a rotation period of the chromosphere with about 140 days. But first I didn't believe it, because there was the technical upgrade of the instrumentation, but my code is rebinning them to the old resolution. So I started to trust that, and it shows that there's a drop in activity in θ1 tau over the last couple of years. And this is how you can use the SIndex for a stable instrument to monitor activity, rotation rate at Iron. Now, Mount Wilson has been decommissioned, but there are several projects that continue the monitoring. For me, I was just using a high resolution spectrograph that I have calibrated for my targets. But it's not well, you don't build about for 700 nanometer wide range to do calcium H&K. No, you build that to hunt exoplanets or do high resolution spectroscopy of oscillating targets. There are other projects that are dedicated to monitor the SIndex, and one of them is the Tigre telescope in Guanajuato. I don't speak Mexican, so but it's actually a German instrument led by Hamburg and by Klaus-Peter Schröder from Hamburg and Mittag from Hamburg, which are collaborating with Mexico. It's a pretty low resolution spectrograph. And we talked yesterday, some amateur instruments get in that range. But you don't need that. You need 5,000 roughly to do the math. But this instrument is dedicated to the follow-up of activity, in particular in late-type stars and giants. And with this, I came to the end. I hope you enjoyed the excursion to UV, and I'm taking the questions.
This one diagram where you had the three, where I said we should concentrate on the three solid curves. Where do they come from? Are they calculated from models, or?
Yeah, exactly. So I tried to give a couple of references. This is Gallet and Bouvier. There is also a Vienna study taking that into account. So what they did was so they try to understand the rotational behavior in clusters. So this is a cluster, this is a cluster. And they took the data points here. Those are the percentiles. I think the 10th, the 50th, and then the 90th. And they were taking stellar models, which are a star is described by, well, by the way, a star is a one-dimensional object on a string. So that's how a stellar physicist treats a star. So we describe that star. And typically, we chop it into two shells, the core and the outer part, and then we let it rotate. And first of all, you put in input physics, you put in chemistry to build your star, to evolve your model along that axis. But then you try to take the two shells and rotate and put some laws that try to explain the observations. So they really try to tune their models to observations. And the dotted line, that's why I say, so this is modeling observations, and the dotted line then is physics, and how much does the core and the envelope couple? And that's an ongoing research topic. We're partly off by the order of 2 to 3 magnitudes, what theory says and what we measure.
Are these all red giant? Red stars, school stars?
This particular study, let me think. Yeah, this particular study is solar-like stars. One solar mass plus minus a bit. The later study, they published a paper, I think 2015, is when they go to lower mass stars, because they have a substantially different depth of the convective envelope. And then you expect that law to be different, but it's the same physics.
What is the mass here?
Mm-hmm.
The mass of the star?
Solar-like. One solar mass plus minus 10-20%.
If you go with your solar stars beyond 100 parsec or so there is the contribution which you get from the interstellar Ca H&K lines. So they would be an offset depending on the position of the stars within the interstellar medium. So how do you correct for that? You resolve the stars, you need a really high resolution. The interstellar lines, you need a very high resolution spectrograph. With a lower resolution, that gets tricky.
Yes, it gets tricky, but I never encountered that problem.
Okay.
For what reason? All the targets we are doing with astrosmology or with, astrosmology targets, those are the ones I study, they are very, very bright. Otherwise, bright meaning brighter than 14.
Yeah.
And then a solar-like star that is 14th magnitude, that can't be far away, because it's intrinsically low luminosity. So I would say the interstellar material is negligible. However, for giants, it is we measure them in the halo, so 100,000 light years away. Seismology works beautiful, in case you're worried. We need to take into account the absorption, that's true, but actually, giants, they have huge peaks, so probably there are other problems there.
Yeah.
You can use it also to measure this line, to measure and quantify mass loss. Because I showed you just the peak, but you saw in the line you have the K1, 2, 3, 4, several features. And the interplay can tell you something about the mass loss of the star and the interstellar component. I think it has a different line because it's much sharper compared to that. And I think
interstellar is sharp.
It's on the, is it to the red?
Well, it depends on the line. The rest velocity is the same for the stellar, but there the differences in the velocities plays a role between the interstellar gas and the star, and then also if you have mass loss there. But the trick is, since the densities are so low, the lines are much sharper than the stellar lines. So
I think let's have a coffee about that. That's
okay.
Which would be the minimum wavelength range of the spectrograph for being able to calculate the SIndex. So,
well.
It should be centered in the UV, but how much range do you need?
Basically, that's your wavelength range you need to cover this regime and this regime. So basically,
30 nanometers, 20 or 30 nanometers range. Because nowadays it is, I don't know for UV, but there are these volume holographic ratings which are very efficient. Has a 90 or 90% of the efficiency, but in very short range.
okay.
And that could be a way of making a spectrograph that just aim to these.
Okay. You don't need and you can gain efficiency by putting a low resolution.
Yeah.
You don't need 100,000. You need 5,000.
Showing us have been results based on investigations or research on these boost lines, particularly the K. What about the also the calcium line in the near infrared area, around 820 nanometers? Can you show us the total wavelength plot? Yeah.
Yeah,
this is the triple line of calcium. What are there also some efforts to use these lines for this kind this comparable sort of research or?
Yes, it is. So it's not only the calcium infrared triplet; it's also H alpha.
Yeah.
They behave similar. The thing is that there you don't see it as the point about calcium K is you see it nicely as a double feature. As soon as you see that, you notice it. For them, the contribution is simply filling up from below, and you need the theoretical modeling of the spectrum that is just taking the photospheric contribution, which some codes give, that you can say, I want combined, I want photospheric, I want chromospheric. If you subtract the purely photospheric Phoenix model, I think what I see in particular is often it's the Phoenix code, where you can say, I want a spectrum for this region with that resolution. Then what you get is, you get the spectrum, you need to repin it, you can subtract it, and the difference between that is so it will be above the photospheric flux. And so you can quantify that. You have it with 3 lines that are in the infrared, good signal to noise, high resolution, all in your favor, except for the line behavior. Same behavior goes for the emission in H alpha. So for those lines, you need very, very strong emissions to actually see it by eye.
Another question: why did you didn't take the moon as a source of light instead of the Earth?
You really want a point source. The moon, yes, but it's not a point source. We want a point source that is fitting and is And you have more inhomogeneity. The asteroids are far away. They're integrated to a point source, but at least for a 1 meter telescope. You don't see it. But the moon, it depends if you point on the Mare, if you point on some white. And frankly speaking, your auto-guiding is not made to guide on the moon. It's made to guide on a centroid. That's the fiber, and you have the wings of the PSF, and it's guiding on the centroid. So, okay. So with this, well, I'm here for the rest of the conference, so if you want to discuss, you're happy to approach me with a coffee. And otherwise, thank you for your attention, and I hand over to the next speaker.